Hello students, in this topic we will study about systems and system properties. What is a system? When we talk about a system has an input, for example input x of t, and an output, for example output y of t. A system can be a discrete time system or continuous time system. In continuous time systems, we have an input x of t, which is continuous in time, and an output y of t, which is continuous in time. For discrete time system, similar, but now instead of having continuous time t, we will have discrete time n. So the input xn and the output yn. A system responds to an applied input signal. So there will be an input and there will be an output. So a system can be, for example, electrical system, mechanical system, control system, industrial system, any industrial process which has an input and an output, and many other systems we have. So, for example, here in this example, we have an electric circuit, and this electric circuit has capacitor, resistor, and inductor. They are connected in parallel, and we have an input current I of t and an output voltage V of t. So if we try to relate the input current and the output voltage, we will have this kind of equation, which has a derivative part and integration part. We call this integral differential equation because it's combining derivative and integration. So we can find also purely derivative differential equation, which has only derivative part. Okay, after we do one more, for example, derivative of the left side and the right side. So this is an electrical system. We can have, for example, a system, an aircraft, where when an aircraft is flying at a certain velocity v, it has a certain control system where there are several input variables and the aircraft should fly at a certain speed, for example at a certain speed v or velocity v, or it should fly at a certain altitude h from the surface of the earth. We have also mechanical systems. We can have also financial systems where we can have a prediction of prices. For example, future prices can be predicted from a certain financial algorithm. So we can have different kinds of systems. Systems can be, for example, a simple single input and single output system, or we can have we can build more complex systems from a single system. For example, in this case, I have system 1 connected to system 2. The input to system 1 is x of t, and the output of system 1 will be an input to system 2, and we will have the final output y of t. This is a series connection of two systems, and we call this cascaded system. And we can have also parallel system. For example, here an input xt, which is input to both system 1 and system 2, and the output of system 1 will be added to the output of system 2 to get the total output y of t. This is parallel system. We can have also feedback system where we have the input to system 1, and then the output may not be the desired output. So the output is fed back to another system, system 2, and then the two are combined, and they will be given to the input to system 1. This is called feedback system, and mostly we find it in control theory. For example, if we want to control the speed of a vehicle, the speed of an aircraft, the altitude or the flight height of an aircraft, and so on, position controlling, temperature controlling, and speed controlling. Okay, so as I said earlier, most systems they are um, characterized by differential equation, which relates the input and the output. For discrete time systems, we have what we call difference equation. For continuous time systems, differential equation. This one we will study differential equation in chapter 2, and also we will study in chapter 3, 4. We have systems described by differential equation. Difference equation in 320 for discrete time systems. Okay, when we study about systems, we have what we call system properties. For example, memory and memoryless, causality, stability, linearity, and time invariance. These are some of the properties. Why we need properties? Because to study properties, because the properties allow us to predict many important behaviors. For example, a linearity property can be used to get the output of a certain input, which is a combination of several other inputs. So by using linearity property, first we find the output for each input, and then we can combine the total the individual outputs to get the total output for a certain input signal. So they are very important. Stability property. Stability property is important because it tells us whether the system is stable or not stable. For example, in control theory, if the system is not stable, if you are controlling, for example, the speed of a vehicle or the speed of an aircraft, if the control system is not stable, then that means you will have, for example, a very high speed which can make the aircraft to crash, or you cannot control the speed of the aircraft, or you cannot control the speed of your vehicle. So if the system is unstable, so these are important properties. So we study each one by one. Okay, what is a memoryless system? A memoryless system is a system where the output at the present time or at time t depends on the input at this time, but not on the inputs from the previous time. Or also, it doesn't depend on the inputs of future time. For example, we can have example a resistor. A resistor. If I have a resistor here, I have an input current IT, and the voltage across the resistor is VR of t. VR of t is R times I of t. If we assume, for example, I of t is the current and VR is the output voltage, then I of t is x of t now, the input, and VR is y of t. The input and the output, they are related. Y at time t is equal to R times x at time t. R is constant. Therefore, the output at time t at this time, at the present time, depends on the input at this time. So this is a memoryless system. If I have another example, for example here, y of t is equal to x of t plus x of t minus 1. X of t means the input at present time t. X of t minus 1 means the previous input. So the output depends on the present input and the previous input, which is not a memoryless system. Not memoryless, or the system has memory, because it has to store the previous input to get the output yt. If I have, for example, here a capacitor, this is a capacitor. The current through the capacitor and the voltage across the capacitor are related by this formula. I of t is equal to C, the capacitance, times the derivative of Vc by dt. Then if we rearrange this, Vc of t that means the voltage at time t is equal to 1 over c, the integration from minus infinity to t I of tau d tau. Okay, we have here another variable tau because we are integrating from minus infinity to t. So we have t in the limit. That's why we have here the integration variable is tau. So if we say now the input is I of t, which is x of t, and the output is vc of t, which is y of t, then y of t is equal to 1 over c from minus infinity to t x tau d tau. What does it mean? It means the output at the present time depends from the previous inputs from the previous time from minus infinity until t, because when we do this integration, the integration limits are from minus infinity to t. So that means the system has memory. So the capacitor is, for this example, has memory. Okay, another property is causality. Causality property. A system is said to be causal if the output at the present time t depends on the previous input or the present input or the combination of the previous and the present input, but not on the future inputs or on the future inputs. So here, all real-time physical systems are causal because time only moves forward. That means effect occurs after cause. So the output at time t depends on the present input and the previous inputs. It's possible in real time. However, how can the output depend on the future time t, on the future inputs? This can be done not in real time, but for example, if you store the input, you can store the input in a computer, and then you can design a system or an algorithm which can depend on the future input because you already store the input data before. So it's possible to design a system or an algorithm which will depend on the previous, on the future inputs. Okay, let's see the examples here. Accumulator system. Y at n, the at time n is from k minus infinity until n x of k. So what does it mean? Y at time n depends from the previous time until the present time. So if I expand this, okay, this equation, expand it. So y at n is x at minus infinity plus x at n minus 2 plus x at n minus 1. This means previous time, x at n present time. So this system is causal. What about if I have y at n 1 over 2n plus 1 summation of from k minus capital M to m xn minus k. For example, let's have m capital M is equal to 2. So y at n is equal to how many samples from minus 2 to 2? 5 samples. So 2 times 2, 4 plus 1. So it's this system is called averaging system. So we are averaging the samples from k minus 2 until 2. So that means y at n is 1 over 5. When k is minus 2, this will be xn plus 2. When k is minus 1, xn plus 1. When k is 0, x of n. When k is 1, xn minus 1. When k is 2, xn minus 2. Y at n depends on xn plus 2. Xn plus 2 is future time. Xn plus 1 is future time. Xn is present time. Xn minus 1 previous time. Xn minus 2 previous time also. So because I have two future times here, that means the system is not causal. Okay, if this summation instead from if it was from minus m until 0, then the system will be causal until 0. Okay, because That means I will have until xn. Okay, stability property. Okay, when do you say a system is stable? Okay, a system is stable when bounded input gives bounded output. That means whenever we give a finite valued input to the system, that means the value of the input is the value of the input is finite. So whenever we give a finite valued input, the output should be also finite for all time t. Okay, which means mathematically, if the absolute value of x of t is less than or equal to a certain constant bx, then the absolute value of y of t should be less than or equal to by. So that means whenever I give bounded input, I should get bounded output. Okay, the value of the output should be bounded, and we call this BIBO, bounded input, bounded output. Okay, and keep in mind this is for all time t. So if this condition is satisfied, we call the system is stable. If not, the system is not stable. So let's see the example here. Let's say x of t, I have a system, and the output of the system y of t is equal to t times x of t. Okay, t times x of t. Y at time t is equal to t times x of t. So let's say we bound the input. So let's say we make the input x of t is equal to 1. So what will be y of t? The y of t will be is equal to t. So for example, if t is equal to 0, y at 0 will be 0. If t is equal to 10, y at 10 will be 10. If t is equal to 100, y at 100 is equal to 100. And if we keep on increasing the time, the output is increasing with time. So in the limit when t is infinity, y at infinity is infinity. That means the output is not bounded. So it keeps on increasing, even though the input is limited. That means the input is 1. The output keeps on increasing. So the system will not be stable. So the system is unstable system. Let's have another example. Let's have a certain exponential system. What does it mean? If I have an input x of t, then the output will be e to the power of x of t. So put x of t to the system, and that at the output you get y of t e to the power of x of t. Is this system stable or not stable? Okay, let's try to bound the input. Okay, so let's the input is between minus bx less than or equal to x of t less than or equal to bx. Then what will be the output? The output also will be bounded between e to the power of minus bx and e to the power of positive bx. So if the input is bounded, the output will also be bounded. So this system is a stable system. Okay. And the other property is linearity property. What is a linearity property? Okay. Linearity property means if I have, for example, by mathematically how we define it, if the input to the system is x1t, then the output is y1t. And if the input is x2t, the output is y2t. Then if I combine x1t and x2t and I create another input x3t, which is equal to a times x1t plus b times x2t. Okay, so I scale the x1 by a. So I scale also as the input x2 by b. Then I created this another input x3, the combination of this. Then if this gives me a y1t plus b y2t, so when I check y3 of t after giving x3t, and if I find y3 of t is equal to ay1t plus by2t, then we call the system is linear. So this is a proof for linearity. Most systems are we have most systems linear systems, so that's why linearity is very important property. And if the system is nonlinear also, we can have an approximate linear, we can linearize a nonlinear system uh, on a certain operating point, okay, on a certain operating point. So that's why linearity property is very important, and it is available in many disciplines, in many fields. So it's important to understand linearity property. Okay, now with example will be more clear. Let's see. Let's say I have a system y of t is equal to t times x of t. So that means this is my system. I give an input xt, and the output is y at t at time t is t times x of t. The question is this system linear? So we follow the procedures to prove this. Okay, first we give x1t. If we give x1t to the system, what is y1t? y1t is t times x1t. If we give x2t, y2t is t times x2t. Let's create another input, x3t, which is a combination of x1t and x2t. So x3t is equal to ax1t plus bx2t. So whenever we give x3t from the relation, from the original relation, let's see here, from the first mathematical relation, whenever we give x3t, the output y3t is t times x of 3t. But what is x3t? We substitute x3t. ax1t plus bx2t. So it will be t times ax1t plus bx2t in bracket. And it means t multiplies both terms. So it will be a times tx1t plus b times tx2t. But t times x1t means y1t from here. And t times x2t means y2t, to y2t here. So that means the output y3t is ay1t plus by2t, which satisfies the linearity property, okay? Because whenever we give x3t, which is a combination of x1t and x2t, that means ax1t plus bx2t, we should get y3 of t ay1t plus by2t, okay? Let's have another example here, x square of t. Okay, is this system linear? Okay, so that means I give x of t and I get at the output x square of t. So let's give an input x1t, we get x1 square t, x2t, we get x2 square t. Okay, then combine the two, ax1t plus bx2t, and create x3t. Okay, if I give x3t from the original mathematical definition, what do we get? If we get x3t from the system, we get y3t x3 square t. Then we substitute the one here, the one we created by combining x1 and x2t. So we make ax1t plus bx2t the whole square, which means a square x1 square t plus 2ab x1t times x2t plus b square x2 square t. Now we compare this value with ay1t plus by2t. What is ay1t? ay1t is ax1 square t plus by2t is bx2 square t. Clearly, if we see this expression and this expression, the two are not equal, which means the system is not linear or the system is nonlinear system. Okay, the system is a nonlinear system. Okay. We have some other examples here. You can follow these examples and try to prove by yourself. And let's say, let's go to the other property, time invariance. Okay. A system is time invariant if its behavior does not depend on the choice of time. That means, for example, if you do an experiment, whether you do it today or tomorrow, if you have the same result, then the system is said to be time invariant. Okay, two identical experiments will yield the same result regardless of the starting time. So how we determine whether the system is time invariant and time variant? Okay, mathematically, if I have an input x of t, it gives me y of t. Then if the input is shifted by time t naught, remember x of t minus t naught means shift of the input by t naught. If t naught is positive, for example, shift to the right, or the input will be delayed. So if the input is delayed, then the output should be delayed by the same amount. Okay? If the input is delayed by 1 second, for example, the output should be delayed by 1 second. If the input is advanced by 1 second, the output should be advanced by 1 second, and so on. So this is how we prove mathematically time invariance property. Okay, which means if I have this is one way to prove. This is the overall system. For example, whenever I give x of t, I have output y of t. Then I delay the output by t naught. When I delay by t naught, I have yt minus t naught. Okay, another way is if I delay the input, okay, so I have a delay system here. So the input x of t will be delayed by t naught, and I will have x of t minus t naught. Let's call this x1t. x1t is x of t minus t naught. Then I get an output y1t. Okay, remember this system and this system are identical, they are the same system. Okay, what I did, I just changed the location of the delay. Okay, I just swap the two, first the delay in the second system, first the delay and the system. Here in the first system, first the system and the delay. Then I compare y1t and yt minus t naught. If I get the same result, then I say the system is time invariant. Okay? If not, the system is not time invariant, or the system is time variant. So y1t should be equal to yt minus t naught if the system is time invariant. Okay? Let's do example. Let's say y of t is x squared t plus 1. Okay, x squared of t plus 1. So is this system time invariant? Okay, let's prove. Okay, so first what we do, now the input pass through the system, and then we delay it by t naught. We delay the output by t naught. So when we delay it, yt minus t naught will be x squared t minus t naught plus 1. And this is the first to prove the first step. And the second step, I delay the input. So let x1t is x of t minus t naught. Okay? So what will be y1t? To get y1t, first I look the relation, the original relation between x of t and y of t. Okay? Whenever I give x of t, I get x squared t plus 1. So whenever I give x1t, I should get x1 squared t plus 1. Okay? x1 squared t plus 1. But what is x1t? X of t minus t naught. That means, okay, x of t minus t naught. That means t plus 1 minus, because this is t plus 1, instead of t, I substitute now t plus 1, t plus 1 minus t naught. So finally I get x squared t minus t naught plus 1. Then I compare these two. Remember, are these two the same? Yes, they are the same. So that means the system is time invariant. Okay. Remember these two procedures. The first one, you have the input, and then the system, and you delay it, and the second one, you delay the input, and then you pass it through the system. Then the two outputs should be identical to be time invariant. Okay, let's have another example. Y of t x of minus t. So at the output, I get x of minus t. What kind of this system is this one? Remember, this is time reversal system. Flip, okay? The output is flipped to get y of t is equal to x minus t, okay? Which means input x of t. Okay, let's do the first step, the first procedure. Input x of t passes through the system. I have y of t, x of minus t. Now let's delay y of t. So t will become t minus t naught. So this t will change to t minus t naught. So x of minus of t minus t naught. Remember, this is in bracket. So minus of t minus t. So minus is for both. So minus of t plus t naught. So I get x of minus t plus t naught. That's the output. Okay. Now, instead of passing through the system first, we delay the input. X of t is equal to delay by t naught and create an output x1t, which is x of t minus t naught. And apply this input to the system. These two systems are identical. Okay? Apply to the system. What does the system do? Okay, whenever you give x1t, it will flip it. So x1 minus t, it will be minus t. So y1t is x1 minus t. Minus t. So x1 minus t, but x1 of t is x of t minus t naught. So what is x1 minus t? The t here should change to minus t. Okay, so it will be y1t is x of minus t naught. Now compare these two, this output and this output. Are these two the same? No, obviously they are not the same because this is minus t plus t naught, this is minus t naught. So since the two outputs are not the same, we call the system is not time invariant, or the system is time variant. Okay. Linear time invariant system. Okay. What is a linear time invariant system? A linear time invariant system should satisfy both conditions, both linearity and time invariant. So mathematically, how we write it? If I give to the system x1t, I get y1t. And if I give x2t, I get y2t. Then I create another input. Okay, this input is both linear combination and there is time shift. You see, x3t is ax1 t minus t naught shifted by t naught plus bx2 t minus t naught. Then the output also should be y3 a y1 t minus t naught b y2 t minus t naught. If this condition is satisfied, then we call the system is linear time invariant, both linear and time invariant. Okay, so these are the steps how to prove a linear time invariance property, LTI property. Okay, LTI property. So we can do example also for this. For example, here I have x of t is equal to another example, y of t is equal to x of t plus 3. Okay, this is for linearity, x of t plus 3, and y1 of t, for example, is x1 of t plus 3, y2 of t, x2 t plus 3, because this is x of t plus 3. Then create another input x3t, a x1t plus b x2t, then y3 of t. What is y3 of t? y3 of t is from the original equation here, x3t plus 3, x3t plus 3, then substitute x3t. x3t is ax1t plus bx2t, substitute here, then I get ax1t plus bx2t plus 3, so that means ay1t plus by2t plus 3, okay? So here ay1t, what about ay1t plus by2t? A times what's y1? x1t plus 3. And what is y2? x2t plus 3. Okay, which means a x1t plus 3a plus b x2t plus 3b. Then, which means again, this means it's not is equal to ay1t plus by2t. ay1t plus by2t is different from y3t, because y3t here, this equation, we need to compare this with this one in order to determine if it is linear or not linear. So here I have ax1t, I have bx2t, bx2t. I have 3 here, but I have here 3a plus 3b. So this system is not a linear system, so it will not be also a LTI system, because LTI system should be both linear and time invariant. So one of the properties is not fulfilled, means LTI property is not fulfilled. Okay, here in the lecture notes I have, for example, here I have a system, and you are told this system is LTI system. Okay, so the system is linear time invariant. So whenever you give x1t this is the input, I get an output y1t this one. Okay, then if I give another input, this one x2t, find the output y2t using linearity and time invariance property, using LTI property. So how we solve this? Originally we are told the system is LTI, okay? And for input 1 I have output y1, and for input 2 what will be the output y2 of t. Then what we should do? We should try to relate this input, the second input, to the first input, and try to write x2t as a linear combination of x1t. Okay, so if we compare these two graphs, we can find that x2t is simply x1t, the original x1t, plus 2 times x1t minus 1. T minus 1 means shift of x1t by 1 to the right. Okay, delayed system by 1. So x2t is x1t plus 2x1t minus 1. Okay, now I write x2t in terms of x1 as a linear combination of x1. Because I am told that the system is LTI, it's very easy to find y2 of t. What should be y2 of t? y2 of t should be y1 of t, okay? Because for x1t, I should get y1t. For 2 times x1t minus 1, I should get y1, 2 times y1t minus 1. Then y2 of t will be the sum of these two signals, y1 of t plus 2 times y1 t minus 1. Okay, and then we plot the graph. So when we plot, we get this. You see, so we use the the LTI property to find the output y2t given the input x2t, x1t, and y1t. Okay, so given what are given? X1t, the input to the system, y1t, the output, and x2t. Then what is required to find y2t? So first step, write x2t in terms of x1t. Then after we write x2t in terms of x1t, then we can write y2 of t by following linearity and time invariance property. Okay, so y2 of t will be y1t plus 2 y1t minus 1, and then finally we plot the result as a function of time. So the x-axis time and the y-axis the amplitude or the value of the signal y2 of t. Okay, so with this we finish the properties, and also we finished the chapter 1. In this chapter we studied what a signal means, and we said we have so many types of signals: electrical signals, sound signals, video signals, and so many types of signals in different systems: electrical systems, mechanical systems, chemical systems, and so on. Signals can be time varying or spatially varying, or it can be both a function of time and space. For example, electromagnetic waves are functions of time and space. And signal can be one-dimensional, so the independent it can be a function of an independent variable time t, or it can be two-dimensional, for example, a function of space and time, or multidimensional. Signals can be continuous time or discrete time. Okay, a function of the time t is continuous and the time t is discrete. And we studied what is power and energy of a signal, and um, uh, we uh, we determine the energy and power of different kind of signals by applying the mathematical formula for energy and power. And we have seen different kinds of signals: periodic signals, complex exponential signals, sinusoidal signals, even signals, or signals, harmonic signals, and so on. And very important, we studied unit impulse signals and unit step signals, which are very important for the next chapter, for example, unit impulse, because it will tell us the unit impulse response of the system or the impulse response of the system. And we studied the property of systems. When we talk about a system, we need to view or look the system from input-output relationship. And we have different kinds of systems: electrical systems, mechanical systems, chemical systems, and so on. And we studied the different properties such as causality, stability, linearity, and time invariance properties. With this, we complete this chapter. Thank you for listening to this lecture.